The last new reaction we're going to talk about in this class, in this whole chapter, is the radical addition of HBr to alkenes. So we've already seen what happens when you add an HBr on its own to alkenes. You get the Markovnikov addition of HBr, and you end up with the bromine on the more substituted carbon. We'll talk about this mechanism in a second. It's a review from 331. Should be familiar to you. But instead of just HBr, we add HBr and peroxides, or HBr and light, or your book even talks about heat, although I'm assuming with heat you get a mixture of both of these mechanisms, so we're mostly just going to see peroxides. You instead get the bromine on the end. So you're still getting addition of HBr to an alkene, but the bromine is going to the less substituted, the anti-Markovnikov position. And one thing that's really, really cool about organic chemistry is that you can use the same reagent under different conditions to get two different products, but the reasoning for both of these is exactly the same. It falls under the same fundamental rules of what we've already learned about organic molecules. So we're going to start with this review of the 331 mechanism. And this is a mechanism we're going to see again in chapter 14. But in this mechanism, we have an alkene. The alkene acts as a nucleophile, or a base attacking the H of the HBr, breaking that HBr bond. Here, everything is 2 electrons, so I'm using our normal 2 electron arrows. And we attack that hydrogen in a way that makes the most stable carbocation. Just like a radical, that means we want the more substituted carbocation. So we have that secondary carbocation and a bromine. That bromine has a lot of lone pairs, and one of those lone pairs is going to attack our carbocation to give us our final product. And the key to this selectivity is this carbocation. We want the more stable carbocation formed. So I'm going to have that mechanism up here in the upper right to compare to the radical addition mechanism. So here I'm going to show the radical addition with peroxides as our initiator, and that's really the only thing we'll see in this class. So here, the first step is our initiator. That OO bond is extremely weak, so it's going to homolize or break in two to give us 2 RO radicals. Those radicals will want to react, and they will react with HBr. I'm only going to show one HBr reacting, but this is going to happen. We have 2 ROs, both of them will react. So that's going to give us ROH and bromine radical. So now we have the bromine radical, which is what's going to react with our alkene. In our second step, I'm going to simplify our alkene a tiny bit here. We're going to react our alkene with our bromine. And again, this is the step that's analogous to reacting our alkene with HBr. We're doing this reaction in a way that we want to form the more stable radical, the more stable reactive intermediate. And so what's going to happen here is that the bromine, because it's being added first, is added to the end to form a stable radical, a secondary radical, instead of the alternative, which is a primary radical. So this part is just like up here, except here we add the H first. So the H gets added to the end to form the more stable secondary carbocation. Here, the bromine's added first to form the more stable radical. So the reasoning is the same, but the outcome is different. This is now going to react with another molecule of HBr to form our final product. So the H will combine with 1 electron from the HBr bond, will combine with that radical to put the H here, and we'll create another bromine radical, which will go on and react with other alkenes. Finally, there are many possible termination steps. We don't even really need to show them all the time. I'm just going to show one option for a termination step, which is that 2 bromine radicals find each other and make Br2. There are many possible options. They generally happen a very small percentage of the time because it's much harder for 2 radicals to find each other than it is for a radical to find an alkene or something else to react with. So one last thing I just want to note here is that this only happens with HBr. HCl, HI, HF, the thermodynamics of this don't work out. So first I want you to try these 2 practice problems. If I don't say peroxides, I'm indicating that it's not a radical reaction. So pause, try both of these, and we'll go over them. So in the first example, we do see peroxides. That means we're looking for the anti-Markovnikov product, which means that we want the bromine to be on the less substituted carbon. In the second example, we don't see peroxides. That means this is going to be an ionic carbocation reaction, and we expect it to give the Markovnikov product, the bromine to be on the more substituted carbon. The last thing I want to do is see how this can be incorporated into synthesis. So this is very similar to one of the synthesis problems we did in our review. I want you to think about this. This is going to be a little bit harder, and we'll go over how to do this together. So what I want you to think is initially, okay, we're starting with an alkane. The only thing an alkane can do is a radical halogenation. And so if we do that radical halogenation with bromine, let's say, you might think we can use that to get all the way to the product, but we can't. Remember, bromine is selective for the weakest CH bond, the most stable radical, so that's going to give this. So this might feel like a failure, but then what you want to think is there any way to be able to turn this into this? You can't move the bromine, that's not a reaction we learned, but how can we put the bromine on the end? Well, one hint is the video we're doing this with, so you can think that this could maybe come from an alkene if we do a radical reaction. So if we use HBr and radicals, we have an alkene. And we have an alkyl halide. So now the question is much more simple. Is there any way to go from this tertiary alkyl halide to the alkene? And that's very easy. That's an elimination reaction. We can do this with any strong base. KOH would work. Potassium ethoxide would work. Potassium terbutoxide would work. It really doesn't matter which one you use. Because we have a tertiary alkyl halide, we're not going to do any sort of substitution reactions. So any of these bases would work. It doesn't matter which one you use. Now, a problem like this is challenging. I'm going to give you as much practice as I can with synthesis. We'll put problems on Canvas. But it does take practice, and it takes a willingness to try things and fail, and then try to rethink the problem in different ways. So I purposely tried to show you here how like a failed attempt might make you likely to see the right answer, how you can work both forwards and backwards, all sorts of things you can do to try to get to the right answer. But again, practicing is the key. It's not something you'll be good at the first time you do it.